Hello again. This is Math 2270 coming to you from the College of DuPage, and the title of this lecture is Vibrations Continued. As always, please be attentive listeners while watching this video. By way of introduction, recall that we were studying the vibrations of a spring. We had carefully set up the problem, discussed the physics of it, and solved the simplest case, a free, undamped IVP. Now we move on to more realistic problems. We begin, or move to next anyway, free damped vibrations. We're still going to assume that there is no external forces acting on the system, with the exception of damping, of course. In this case, the differential equation, as we discussed, would be m u double prime plus gamma u prime plus ku equals 0, where m, gamma, and k are all positive constants. M was the mass, gamma was the damping constant, and k was the spring constant. So upon solving for the roots of the characteristic equation, you get that R1 and R2 are going to be respectively minus gamma plus or minus gamma squared minus 4mk all over 2m. Now there are three cases here depending on the value of the discriminant. It's either 0, bigger than 0, or less than 0. Let's look at the first case where gamma squared minus 4mk, the discriminant is equal to 0. Now in this case we will get a double root from the characteristic equation, and the displacement at any time t will be u of t is equal to c1e to the minus gamma t all over 2m plus c2t e to the minus gamma t over 2m. Now notice that as t goes to infinity, both those exponentials go to 0, so the displacement will approach 0, and so the dampening does work. Now this case is called critical damping, and this will happen when the damping coefficient is 0, and that is that gamma squared minus 4mk is equal to 0, or gamma squared equal 4mk, or taking the square root, gamma is equal to 2, the square root of mk, and this is called the critical damping value. The value of the damping coefficient gives a critical damping, and it's called the critical damping coefficient, and it's denoted by gamma sub CR for critical damping. Let's look at the case where gamma squared minus 4mk is greater than 0. Again, the discriminant is greater than 0. In this case, we'll rewrite the roots a little bit. R1 and R2 then are going to be, as before, minus gamma plus or minus the square root of gamma squared minus 4mk all over 2m. But if we factor a gamma out from the square root, we get this minus gamma plus or minus gamma square root of 1 minus 4mk over gamma squared over 2m. And I can factor out the gamma over 2m, the minus gamma over 2m. I get 1 plus or minus the square root of 1 minus 4mk all over gamma squared. Now, notice from our initial assumption, which was up here, that gamma squared is greater than 4m. And we also then know that this is also less than 1, and we get that because if we were to divide both sides of this by gamma squared, we have 1 there, and we have 4mk over gamma squared. So using this, you can see that the fraction under the square root here, this is less than 1, that is 1, and so you're taking a number that is positive, less than 1, so what is under the square root is less than 1, and if the quantity under the square root is less than 1, that means that the square root of this is also less than 1. In other words, this value is less than 1. And you can say, well, why is this important? Well, the quantity in the parentheses tells us that now 1 plus or minus a number is less than 1. That means that what's inside the parentheses up here is guaranteed to be positive. Think about this. And so the two roots in this case are guaranteed to be negative. So therefore R1 and R2 are still negative exponentials, And again, as t goes to infinity, this will approach 0. So the damper again does what it's supposed to do. So this case will occur whenever these values happen. And gamma, of course, is bigger than, gamma squared was bigger than 4mk, so gamma is bigger than 2 square root of mk, and that is what the damping critical value was. So gamma is here, and it's called over damping. The final case is when the discriminant gamma squared minus 4mk is less than 0, and you're going to have complex roots here. And we know if we call this lambda plus or minus mu I, and by the way, the real part is guaranteed to be negative because it's minus gamma, that's the real part. And the complex part comes from this. And so the displacement is u of t is equal to c1 e to the lambda t cosine mu t plus c2 e to the lambda t sine mu t. You can factor the e to the lambda t out of there. And remember that we talked about writing this as r e to the lambda t cosine mu t minus delta. And again, that's a question I sometimes ask on the high stakes assessment, is to have you do that. Notice that we reduced the sine and cosine now, which was here, down to a single cosine, as we did in the undamped case, the example we did last period. So also, I guess, since lambda is less than 0, this displacement will approach 0 because that will be the dominant thing. So the dampener also works in this case. But here you have that from up here, that gamma squared is less than 4mk, so gamma taking square roots of less than 2 square root of mk, which is the critical coefficient. This is called underdamping. Okay, let's finally look at some examples of this. Now we're going to take the spring and mass system from the first example that we did. I repeated it here. So a 16-pound object stretches this spring 5/2 feet by itself. There are no dampening and no external forces acting on the system. We do have an initial displacement 6 inches upward from its equilibrium position, and we're given an initial velocity of 1 feet per second downward. So we're going to find the u of t. But now what we're doing is we're evolving this and we're attaching a damper to it. So this damper will exert a force of 12 pounds when the velocity is 2 feet per second. Find the displacement at any time, u of t. Pause the video and give this a try, and we'll see how you did. Let's see how you. So the mass and spring constant were already found in the first example, and we don't have to do that work again here. We do need to find the damping coefficient, however, and to do this we use the formula for the damping force with one modification. The original damping force formula was F sub d is equal to minus gamma u prime, but remember that the force and the velocity are always acting in opposite directions. So if the velocity is upward, negative according to the way we set it up, the force will be downward, that's positive, so the minus in the formula will cancel against the minus in the velocity. And likewise, the same thing will happen if we change things around. So you see, this is always going to be positive because they will be different SIG ends. So FD, the force relative to dampening, is gamma times u prime. Now doing this gives the following for the dampening coefficient then. So 12 is equal to the dampening coefficient times 2. That means gamma is equal to 6. So the IVP for this example then is 1/2 u double prime plus, now there's where the 6 comes in, u prime plus 18u equals 0. U of 0 equal minus 1/2, and u prime of 0 equal 1. You should fill in the steps, but you know how to solve this. So there was the IVP again, and we can check to see that the damping coefficient was 6, so we have critical damping here. And that means that we're going to solve the differential equation, but this time we expect to get a double root. And so if we solve this, and you should do these details because it's good practice for the midterm and for the final, but u of t is going to be minus 1/2 e to the minus 6t minus 2t, there's the t, e to the minus 6t. Here's a sketch, and you see you start here, you let it go, but it really doesn't vibrate. Notice the vibration really is not a true vibration as we tend to think of it. In the critical damping case, there isn't going to be a real oscillation about the equilibrium point we tend to associate with vibrations. The damping system is strong enough to force the vibration to die out before it ever really gets a chance to do much in the way of oscillation. Let's look at another example. Again, we're going to take the spring and mass from the first example, but this time we're changing the damper, and we're going to have it so that it exerts a force of 17 pounds when the velocity is 2 feet per second. And you want to find the displacement at any time. Again, I repeated the first example here so you can look at it. Pause the video and give this a go. Let's see how you did. Now, the only difference between this example and the example 2, previous example, is the damping force. So we look at the damping coefficient. 17 is equal to gamma times 2, and that means this is 8.5. But now this is bigger than the critical damping. So it looks like we've got over damping this time. So we'd expect to get 2 real distinct roots from the characteristic equation, and they both should be negative. So the IVP for this example then is 1/2 u double prime plus, there is the 8.5 or 17 over 2 u prime plus 18u is equal to 0, and the same initial condition. Now this one is messier than the previous example, and we'll do a couple of steps, but I think students should work through all of them and make sure you follow this. It'll be good preparation for high stakes assessment. Well, leaving it to you to fill in the blanks, but the roots this time are going to be R1 and R2 is minus 17 plus or minus the square root of 145 over 2. Now, engineering problems sometimes need calculators, and this would be one that calculators would be required. So if we do those two values, we get these as the approximations we're rounding off. And so we convert to decimal and go that route. And again, you can see that there are 2 real distinct roots, and they are both negative. And so the general solution is, here's with the C1s. And here is when you plug in the initial conditions, you get those as coefficients. And here's a sketch of the displacement for this example. Again, this is over damping, and you see that again, not much in terms of an actual vibration. Now note an interesting thing does happen here though. Even though we are overdamped in this case, it actually takes longer for the vibration to die out than in the critical damping case. Sometimes this happens, but it's not always the case that overdamping will allow the vibration to continue longer than the critical damping case. Also notice that, as with the critical damping case, we don't get a vibration in the sense that we usually think of them. Again, the damping is strong enough to force the vibration to die out quick enough, so we don't see much, if any, of the oscillation that we associate with vibrations. Let's look at another example before we move on to the next type of vibrations. Okay, so what we're going to do is take this spring and mass again from the first example, but we're going to attach a damper to it that will exert a force of 5 pounds when the velocity is 2 feet per second. Find the displacement, and again, I repeated example 1 here if you want to recall that. So please pause the video, give it a go, and let's see how you did. Okay, so again, we find the damping coefficient 5 is equal to gamma times 2, so this is 2.5. This is less than the critical damping, so it is under damping this time. And it shouldn't be too surprising given the first 2 examples we're covering this, but this time you will have some oscillation that will happen. So the IVP that this leads to is 1/2 u double prime. There's the 5/2 u prime plus 18u is equal to 0. There's the same initial conditions. Now in this case, and you should check this, but the roots are going to be -5 plus or minus the square root of 119 times I over 2. These are complex roots as we expected, and that's going to cause an oscillation. So the general solution is u of t is equal to e to the minus 5/2 t, and this is c1 cosine square root of 119 over 2t plus c2 square root of 119 over 2t. And if you plug in the initial values, and I encourage you to do this calculation, you will get that this one is minus 1/2, and this one is this number, and that is rounded off. And again, we can convert this to a single cosine. I do expect you to be able to do this, and we get that r, the amplitude, is going to be this rounded off, 0.502096, and the phase shift is going to be the inverse tangent of the ratio of these two numbers, the coefficient of the sine over the coefficient of the cosine. We get that. Now that tells you that this is, it's a positive number, but that means either it is in the first quadrant here or it's in the third quadrant here, and you don't know which. But as in the undamped case, you can use the coefficients of the sine and cosine to determine which phase shift you should use. Again, you have to be engineers, just don't take the value from the calculator. So the coefficient of the cosine, C1, is negative, and so cosine of delta must also be negative. Likewise, the coefficient of the sine, C2, is also negative, so that must be negative. So negative and negative means that we're in the third quadrant, and this is the one that we use for the phase shift. So the displacement then, and now we're really just using it here, so this is the amplitude times e to the minus 5t over 2, and that's cosine this, and there's your phase shift. And so here's a sketch of the displacement, and you see we do get a little bit of oscillation before things die out. So there is a true vibration, and this is the point of critical damping. As we increase the damping coefficient, the critical damping coefficient will be the first one where a true oscillation in the displacement will not occur. For all values larger than this, we will also not see true oscillation, but less than this, we do see true oscillation. Now, from a physical standpoint, critical and overdamping is usually preferred to underdamping. Think of the shock absorbers in your car. When you hit a bump, you don't want to spend the next few minutes bouncing up and down while the vibration set up by the bump will die out. You would like there to be as little movement as possible. In other words, you want to set the shock absorbers in your car to get the least critical damping so that you can avoid oscillations that rise from the underdamped case. Okay, but now we're going to move and look at cases where there is other external forces that act on the object in the system. And this is forced vibrations, and we're first going to look at undamped forced vibrations. So here, again, the difference is we have an f of t here. There's no first derivative term because it is undamped, but we're going to be talking about what happens when there's an external force out here. Now this is just a non-homogeneous differential equation, and we do know how to solve those. In fact, we know multiple ways to solve those. The general solution then will be the complementary solution plus the particular solution. And the complementary solution is a solution to the free undamped vibration case. To get the particular solution, we can either use annihilators or variation parameters, and that depends on what the forcing function is up here. Okay, now there is a particular type of forcing function that we're going to look at here because it leads to some interesting results. Suppose that the forcing function is a simple periodic function of the form capital F of t is equal to capital F0 times cosine of omega t. Now omega, as you know, is a frequency, and that's and we have a natural system frequency, but we're going to say this is either sine or cosine. Now for the purposes of this discussion, let's just use the first one. Now, so the IVP then becomes this, but instead of f of t, we put f0 times cosine omega t. And the complementary solution, as pointed out above, is just the complementary solution is c1 cosine omega 0. That is the natural frequency of the system, plus c2 times sine omega 0 t, where again, omega 0 is the natural frequency. Okay, we need to find a particular solution, and we know how to do that. You either annihilate the right-hand side or use variation of parameters and things. But you see, there's a difference if omega 0 is omega and if it's not omega. Now, if it's not omega 0, so omega of the right-hand system and in this particular solution is not the system frequency, then it's all okay because we can proceed to solve this. And when we do, let's just say annihilation, because we could annihilate that and set the coefficients equal, we find out that A and B are these numbers. And so everything is good. And so the particular solution ends up being this number. That was the coefficient times cosine omega t. And we could simplify that a little bit if we cared to. And you see that there is a denominator, though, that is omega 0 squared minus omega squared with the simplification. Now, the thing that you want to realize is you got to stay away from 0 in the denominator. But that means that we now have the complementary solution plus this solution, and things are good. Now, if we had used the sine form of the forcing function, we get a similar formula. But let's look at what happens if omega 0 equals omega. Well, a particular solution this time, whenever you do that, since they equal each other, there's going to be a t added to the particular solution. So you have a t cosine omega 0 t and b t sine omega t. Okay, so that's what we're doing, and we start working this and through to get a solution using annihilators. But this time, what will happen is that there's some serious issues that will happen as t increases. And remember, there was a t in this solution. The addition of the t in the particular solution will mean we're going to see an oscillation that grows in amplitude as time goes on, and eventually it will destroy the system. This case is called resonance, and you really would generally like to avoid this at all costs. Now, resonance arose when we assumed that this frequency equals the natural frequency, and the same thing could have happened if we had a sine. So engineers want to take care that you don't have forcing functions that are either of these forms, and they come in a variety of forms. If you do run into a forcing function different from the one used here, you'll have to figure out if you do have a problem with resonance before you destroy the system that you've built. Let's look at a problem and see what really happens with resonance. So here we have a 3 kilogram object attached to the spring, and it stretches the spring 392 millimeters by itself. Again, notice the units here. There's no damping in this system, but the forcing function is of the form f of t equal 10 cosine omega t. It's attached to the object, and we're telling you in the problem that this will experience resonance. So you see these do match. So if the object is initially displaced 20 centimeters downward from its equilibrium position, and again, you've got millimeters and centimeters and kilograms, so you need to sort that out, downward from its equilibrium position and giving a velocity of 10 centimeters per second upward, find the displacement at any time t. In many ways, more involved. So please pause the video and give it a go. Let's see how you so we need to find K here because we didn't tell you what K was, but we recall that K is mg over L. So 3 kilograms, 9.8 meters per second squared, and this is millimeters, so it's 0.392. So you get K is 75. We were also told that the system experiences resonance. So the natural frequency is going to be omega 0 is equal to the square root of K over m, which is going to be 5 in this case. So the IVP for this problem is 3 u double prime plus, and then this is going to be 75 because that is 75u because that's the spring constant. This is equal to 10 cosine of 5t. Now notice we have 5t here because that is the resonance frequency, and here are your initial conditions. Now this is not a difficult problem for you to solve, and so you should do that. Now when you do, you'll find that you have u of t is equal to c1 cosine 5t plus c2 sine 5t plus, and now you get this constant, but then this is going to be t sine of 5t. So you see the t does appear here, and that's the thing that causes the problem. And then when we do some simplification and plug in the initial conditions, you get that u of t is equal to 1/5 cosine 5t minus 1/50 sine 5t plus 1/3. There's the t again, sine 5t. And if we change this into the, we change the complementary solution into r cosine of theta, what we're going to find out that the displacement becomes u of t is equal to, there's the amplitude, there's the phase shift, again we're using this one this time, plus 1/3 t sine of 5t. Now what happens, my dear students, is this is what happens. So you see it continues to oscillate, but the t, as t gets bigger and bigger, the oscillations get wider and wider, and eventually you destroy the system. Let's look at one final vibration case. And we've got everything in here, so this is going to be m u double prime plus we have damping u mu prime plus k, there's the spring constant u, and we have an external forcing function. And there are a couple things that we know, but when we work through this example, we're going to, the complementary solution will approach 0 as t increases. And because of this, the complementary solution is often called the transient solution in this case. But also, because of the behavior, the displacement will start to look more and more like the particular solution as t increases. And so the particular solution is also often called the steady state solution or forced response. So here's an example. Take the system from the last example, which is repeated here. But this time we're adding a damper that will exert a force of 45 newtons when the velocity is 50 centimeters per second. Now please give it a go. Let's see how you did. Okay, so FD is gamma U prime. So 45 is equal to gamma times 1/2, and so gamma is 90. And so that means we end up with this problem. This is our IVP. 3u double prime plus 90u prime plus 75u is equal to 10 cosine of 5t, as had we had before, and the same initial conditions. Now the complementary solution then for this one, and again we do have the dampening, so what we get is u sub c is equal to c1 e to the minus 15 plus 10 square root of 2t, and c2, or plus c2e to the minus 15 minus 10 square root of 2t, and you can simplify that, and we just plug that into a calculator for the approximation here. So for the particular solution, it'll be of this form once you do annihilation, and you can plug into the differential equation and equate the coefficients. You see there's no sign here. But that means that and when we set the coefficients equal, we figure out that UP is, now there was no sign here, but there was a sign in our original thing. So what we get is we get a 0 for A, but B is 1 over 45. So the particular solution that we get here is 1 over 45 sine of 5t. So the general solution then is the complementary solution, which you can see will go to 0 as time goes on, plus 1 over 45 sine 5t. And if we apply the initial conditions, we can figure out what C1 and C2 are. And so here's, and you can see that eventually there's a steady state solution and your transient solution dies out over time. One more footnote. As we mentioned, and this means I'm just really trying to show you that you get pretty much the same differential equation and you can solve circuit problems too. This is called a inductance, resistance, capacitance series circuit. And so many different physical systems can be described by linear differential equations similar to the one we had. And so this is the one that we were studying. But here's the one we get. So you see the role of the mass is played by the inductance. Here's a picture of what the circuit looks like. The role of the damping as coefficient happens is the resistance, which is here, and the capacitance, 1 over the capacitance, plays the role of the spring constant. So you can see it's really very much the same differential equation to solve. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. God bless you all, and look forward to seeing you in class.